Welcome for the second day of the Future Composite Conference. I think today is going to be a very busy day because I have to say that we have an exceptional list of speakers for the afternoon, and I'm very glad to make the introduction for the first presentation of this afternoon, that is a keynote given by Professor Michael Wisnom. So it's an honor to give the introduction to Michael today. So Michael is Professor of Aerospace Structures at the University of Bristol. He is director of the Bristol Composite Institute, which builds on the work of the Advanced Composites Collaboration for Innovation and Science, which he founded in 2007. So Michael is a well-known leading expert on the mechanics and failure of fiber reinforced composites with more than 400 published papers. He is a member of the steering board of the UK National Composites Centre. He is editor-in-chief and European editor for applied science and manufacturing of the international journal Composite Part A, and he was director of the Rolls-Royce Composite University Technology Centre. Michael is a fellow of the Royal Academy of Engineering, of the Institution of Mechanical Engineers, and of the American Society for Composites. He received the Royal Society Wolfson Research Merit Award in 2005, and he was president of the International Committee on Composite Materials from 2009 to 2011. So Michael is an exceptionally accomplished scientist who is going to give today a keynote on thin-ply hybrid composite with pseudo-ductile response. So I will stop sharing my screen to give the floor without losing more time to Michael. Michael, I think you can share your screen now.
Excellent. Thank you very much for the invitation and the introduction. I'm really delighted to be here to talk to you a bit about our research. It would have been great to actually come and visit, but anyway, I'm pleased to at least present what we've been doing in the last few years. So we have a very large research centre in Bristol working on fundamental research at the university, and we also have very close links with the National Composites Centre in Bristol, and as Enrique mentioned yesterday, where we develop technology in the university and work with NCC in terms of the application and scale up and demonstration. But today I'm going to give a specific talk on one of the really exciting areas of research over the last few years, where we've had this very large grant on looking at creating a new form of composite materials based on thin-ply hybrids with a pseudo-ductile response. So this is a large program in collaboration with Imperial College, which is now finished, and I'm going to give you a summary of some of the work on how these thin-ply hybrid composites behave in different loading modes: tension, compression, and bending. So carbon fiber composites are great materials. They're stiff, they're strong, they're light, they're durable, they lack corrosion problems, but they do have a problem. When they do fail, it tends to be a sudden and catastrophic failure, and that's a really undesirable aspect of the composites. So the question arises, can we add metal-like ductility? So we keep the benefits of the high-performance composites, but actually introduce a more gradual failure. So that was the challenge in this program, the HyperDuct program, where we wanted to create materials which show the great response of composites, but have some sort of ductile or pseudo-ductile response. So we looked at a number of different approaches to this. We looked at whether we can create this additional strain by means of fiber reorientation. We have angle plies, and they can scissor. That produces additional strain over and above the strain in the fibers, giving a nonlinear response and some additional strain and more gradual failure. We looked at strength dispersion, for example, fragmentation in plies. And we also looked at aligned discontinuous composites, where we can get slip at the interfaces, which can create additional strain. And the HyperDiff program, which was mentioned yesterday by Enrique, the HyperDiff method for aligning composites, short fiber composites, came from this program. And we were using it originally, it was developed to create these pseudo-ductile responses and to look at hybrid materials. But we found it was a very effective method for producing materials with just one fiber, and particularly giving the ability to use recycled composites. And then the final one was the ductile fibers, which was work was done at Imperial College on creating carbon fibers themselves exhibiting ductile response based on carbon nanotube fibers. So that was in the overall program, but today I'm just going to talk about this second theme, where we use hybrid composites to create a pseudo-ductile response. And I'm going to cover the behavior of these pseudo-ductile thin-ply hybrids in tension, how they behave in fatigue, what happens when we load them in compression, and also in bending. So starting off then with the basic concept of these pseudo-ductile hybrids, what we're doing here is combining a high strength material, so a high strain material such as glass, and a low strain material such as carbon. So the glass has got a lower modulus but a higher strain to failure, and the carbon a higher modulus but a lower strain to failure. And if we combine those together in an interlayer hybrid, then we can produce a material, if we do it right, which shows this sort of stress-strain response, which is much more similar to a yielding metal than what was typically seen by a high-performance composite. So how do we do this? Well, we have to consider the different damage modes that we get in these hybrids, and we have to do the design the right way to get this behavior. So if we start off with, if we have too much carbon, then what happens is when the carbon breaks, then the glass will break as well, and we'll get a catastrophic failure. If we put a bit less carbon in there, when the carbon fails, then we'll get a delamination at the interface, but again, we'll get a sudden load drop, which is not what we want. But if we also make that carbon layer thin, then there will be not sufficient energy to propagate the delamination when the carbon breaks, and therefore we can get this multiple fragmentation, shown schematically here, which gives a plateau on the stress-strain curve. And this can be combined with a bit of localized delamination around the breaks, which give us this gradual failure that we want without a catastrophic delamination or fibre failure. So what does this depend on? So we developed these damage mode maps, which show how the different combinations of materials create the pseudo-ductility and the right failure mode that we want. So it really depends on two parameters. In this case here, I'm showing this for a S-glass and high-strength carbon combination, but we can produce these maps for any material combination. And you can see on the bottom axis, we've got the carbon-glass proportion. And the second axis is the absolute thickness of the carbon layer. So if we have too much carbon, we get this premature failure, the whole thing fails catastrophically. If we have less carbon, but it's thick, then we can get this catastrophic delamination. Neither of these are what we want. But if we have sufficiently thin absolute ply thickness and not too much of the carbon, then we can get this fragmentation and delamination, or just fragmentation on its own. And this gives us the pseudo-ductile gradual response which we want. And the colors represent the amount of pseudo-ductile strain. So we can get, if we're in this region here, close to this transition, we can get 1 to 2% of pseudo-ductile strain, additional strain over and above the strain in the carbon. Of course, we don't want to be too close to this, otherwise we risk going over into the catastrophic failure modes. So we want to be in this region, not too close. So, showing the results for that combination of S-glass and thin, high-strength carbon. In this case here, we've used 2 layers of 0.03 millimeter carbon. So we've got 0.06 millimeters of carbon sandwiched between standard thickness S-glass. And you see we have this very nice plateau on the stress-strain curve. And in this particular case, we get about 1.2% additional pseudo-ductile strain beyond the point at which the carbon fibers start to fail. Another interesting aspect of this is this pattern that we see on the surface. So the laminate is initially black due to the carbon, but when it fragments and we get delamination, then you see these patches appearing because the light doesn't get past the interface between the glass and the carbon. So this is a very nice way of visually demonstrating that we've exceeded the pseudo-ductile yield point, and is very promising as a way of indicating an overload. So as well as producing these nice pseudo-ductile stress-strain curves, we have an indication that it's been overloaded. And this can be used as a damage sensor, either as part of the surface of the structure or as a separate bonded-on sensor, which could be used indeed with metal structures as well as composites. We can also do the same thing with all carbon hybrids. Rather than using carbon and glass, in this case here we've used two different grades of carbon. We've used an XN80 high modulus carbon and a T1000 intermediate modulus, in both cases thin plies. And again, we see this pseudo-ductile response here with a plateau and about 1% of additional pseudo-ductile strain. We can make these into quasi-isotropic laminates, and there are two ways that we can make a hybrid. We can do it by dispersing the material. So in this case here, we've got a hybrid sublaminate of 45 glass, 45 carbon, and 45 glass. And that 45 hybrid sublaminate then is repeated with different orientations through the thickness. So that's a material dispersed laminate, or we can do it this way, where we disperse the orientations but keep the materials together. So we have a quasi-isotropic glass, and then a quasi-isotropic carbon, and then a quasi-isotropic glass. And both methods work and have different advantages and disadvantages, but generally this one we think is better, the orientation dispersed, because it produces less edge delamination, which can be another critical failure mode in composite structures. So you see with this quasi-isotropic laminate, this time it's a 0 ± 60 layup, we see the same pseudo-ductile response with a bit of a plateau, additional strain, and we can load this in any of the fibre directions and we get a similar response in each of the directions. One of the key features of this produces notch insensitivity, because we can suppress the stress concentrations. If you have a hole or a crack, the stresses are very high next to that hole or crack. But this pseudo-ductile response redistributes load in the same way as yielding would in a metal structure. So in red, showing here the response of the unnotched specimen. And you can see that with the notch, whether it's a hole or a crack, then we get up to the same point where the yielding starts in the gross unnotched specimen. But in this case here, then that allows us to get right up to that pseudo yield stress without failure. And bearing in mind that actually around the edge of the hole here, it's reached this yield stress right down here. And all along here, as the load is increasing, we're seeing damage developing around the hole locally, redistributing the load and allowing us to go right up the way here before we get a final failure. And you can't see it very clearly here, but there's already damage around the hole. And then as the strain increases, this propagates until at this point here, you've got full failure across the width of the section. So this is a very desirable characteristic to make the material less sensitive to notches and other stress concentrations. We've also done work on looking at the fatigue performance, which is actually pretty good. And in this case here, it's another different fibre, but a similar high strength thin carbon sandwiched between glass. So the first thing is we established the baseline knee point. So we have this nonlinear stress strain response. We establish that knee point, and then we can fatigue it at a level below that knee point and see how it performs. Those fatigue tests then were done in sinusoidal load control at 2 Hertz with an R ratio of minimum to maximum stress of 0.1. And you can see that at 80% of that knee stress, there's no visible damage or noticeable change in stiffness even after 100,000 cycles. So if you keep the stress below that pseudo yield point, then they're very good in fatigue. You take the stress a bit higher, then after some time you do start to get some failure. So at 30,000 cycles, at 90% of that knee point, then you do start to see some failure, because at 90% of the knee point, there's already a little bit of damage in that carbon, and it does eventually start to spread. We've also looked at the point of actually loading it beyond this pseudo yield point. So initially we preload it up to this point. We go beyond that yield point, so introducing damage. So we've already got these fragmentation events have occurred. We've got fragmentations in the specimen. And then after that, after we've put that damage in, we fatigue it at some proportion of that knee point stress and see what happens. So at 80% of the knee point stress, you see that the damage does spread after a few thousand cycles. Then we start to get propagate. And eventually the whole specimen delaminates, but it's still able to carry load because the glass is intact. And if you look at the different levels here, plotting 70, 80 or 90% of the knee point stress, and you can see that at 90% of that knee point stress, it delaminates after a few thousand cycles, but at 70% it goes for a few tens of thousands of cycles before it delaminates. So overall, this fatigue performance looks quite good. What about compression? Well, when we started this project, we were looking primarily at the tensile performance, and we were not expecting this mechanism really to work in compression. So that was the question that arose: can you get fragmentation under compression as well as in tension? So initially, we looked at this by doing a bending test and just putting one layer of this hybrid material on the surface here, on the compression surface. In this case here, we're using, again, S-glass with a thin M55 high modulus carbon on the surface. We loaded it up and measured the strain based on fitting points on the edge of the specimen and working out the curvature from that. And what we see is we got a distinct change in slope at 0.5%, which is the compressive failure strain of this M55 fibre, and then again it's linear beyond that. So to understand what was happening there, we did some interrupted tests where we took them to 1.2% strain, so well beyond this knee point, to look at what the damage was in the specimens. And we had a little jig here, so we could actually load it and unload it under the microscope to look at the development of damage. So here you see the top view of the specimen, and it has this similar sort of pattern that we saw in tension, a bit more fine, but similar sorts of patterns here indicating that fragmentation has occurred here under compression. And if we look at the side, you can see these angled cracks at quite regular repeating intervals in that carbon ply close to the compression surface of the specimen. Now, if you look at those, you can consider this a little bit like a fragmentation test. In tension, you have a critical length of a fibre, or this can be applied at the ply level. And if you work out the length required to get load into the ply by shear, then you can work out this critical length, which is a function of the modulus, the compressive strain to failure, the thickness of the ply, and the interfacial shear stress. So if you put the numbers into that equation, you work out that the critical length should be about 1 millimetre. But actually, these fragments have a much closer spacing, with an average of about 0.4 to 0.5 and a distribution of those. So the fragments are much shorter than the critical length. And what that tells us is that the plies are still carrying load. After they fragment, they're still carrying load. So I guess that's not surprising because they're in contact. But then the question is, well, how do we get this additional strain if they're in contact and still carrying load? Why do we get additional strain? So to look at that, let's look at this magnified version of what happens at the crack tip. So here you've got an angle crack, here unloaded, and if you look at the interface there, you can just about see there's a delamination which is starting, but it's closed. But if we put the strain on at 1.2%, then you can see that delamination has opened up, and the same down here. So what's happening is we're getting a wedging action, which is causing that delamination to open up. And if you look at higher magnification, you can see that unloaded, those fibres line up approximately. But when you put them under load, you can see that they displace this way, but because of the angle, there's also a displacement in this fibre direction. So that produces a bit of additional strain. That's what gives us this pseudo-ductile strain that we get in compression. So showing that schematically, we have the crack, which is typically at some sort of angle, and it's not a nice smooth crack like that, but conceptually we have a crack and some sort of behaviour where it can slide, albeit with friction and resistance, and then here we have a potential delamination opening up. But provided we keep this ply relatively thin, then there will not be initially enough energy to make that crack propagate. So this will be stable. But at a certain point, and especially it depends on the ply thickness, this may propagate. And then we would get an unstable failure. So to look at this, we did tests in direct compression using the same M55 carbon and S-glass materials. But in this case here, we've got a layup where we've interspersed the carbon between the glass all the way through the thickness of the specimen. And we've varied the number of carbon plies here to have either single, double, or triple carbon of thin 0.03 millimeter ply between the S-glass plies. And then we've tested them in the Imperial College rig and looked at how they behave, measuring the strain with both a strain gauge and an extensometer. So this is the response. So you can see that we do get a nonlinear response with a change in slope at about 0.5% strain, which is the compressive failure strain of these carbon fibers. With the triple fiber, you see that as soon as that fragmentation starts, the whole specimen fails. But when we have two or one ply together, then we get a change in slope. It still increases, but then at a certain point, it fails due to the delamination, but at a much higher strain. So this behavior is similar to what we saw in tension, but on tension, we saw a plateau, but in compression, we still see a secondary slope here. And that's because the carbon is still carrying load and can still continue to contribute much more than it can in tension when we have these fragmentations and unloading of the carbon plies. We look at the specimen here, then we have the fragmentation occurring at this point here. Then we go quite a lot further, and at this point where there's a load drop, then one of these surface plies has delaminated. You go a bit further, and the one on the other side delaminates, and then shortly after that, the whole specimen collapses, and we get complete failure. So that's what's happened when we have a single ply of carbon. And we get similar with the double ply, except it fails a little bit earlier. So moving on then to look at the flexural behavior. So here we're taking the same 0.03 millimeter M55 high modulus carbon and the standard thickness S-glass plies, but now we're laying them up right the way through the thickness and testing them in 4-point bending. Again, we've changed the number of these M55 plies to be either a single ply or a double ply. So what you see here is that, first of all, we see a fragmentation in compression at about 0.5% strain, the compressive failure strain of the fibers, and you can just about see there's a bit of a change in slope. It's not very dramatic, but we do get fragmentation in compression starting here. And then later, at a slightly higher strain of about 0.8%, then we get the fragmentation in tension. This is much more visible, and we get similar behavior whether we have a single or a double ply of carbon. And we get substantial nonlinearity before the final failure occurs in compression. If you look at the specimen afterwards, you'll see on the compression side, we have these characteristic angled cracks, which look like shear cracks going through the ply. If you look at the tension, we get quite a different type of response, because there we have the tensile fiber breaks, and they don't all line up. So we've got different fibers are broken in slightly different places, but they're still relatively close together and can interact to form some sort of staggered crack. So then we change the fiber to go, instead of having an M55 high modulus fiber, which has a relatively low strain to failure, we put a TC35 high strength carbon epoxy instead. So the setup is the same S-glass standard ply thickness with one or two of these high strength carbon thin plies sandwiched between them and loaded in 4-point bending. So again, we see a high nonlinearity, but this time we only get fragmentation in tension. But because of the much higher failure strain of this TC35 carbon fibre, we don't see any fragmentation in compression. We get fragmentation on the tension side, and you can see that gives a substantial change in the slope, and we get these quite high strains, and final failures by compression. But look at the strains here. 3% strain is a very, very high failure strain for a carbon fibre material. That's 2 or 3 times what you typically expect for this sort of material in normal direct compression. And that's for several reasons. One reason is because it's a bending specimen, and the bending specimen, the strain gradient through the thickness can increase the failure strain. But also, we think there's a hybrid effect in that the carbon fibres are supported by the adjacent glass, and therefore this inhibits the shear instability microbuckling type of failure which you typically get with carbon fibre. And you'll see that the strain actually is higher when we have a single carbon fibre layer to a double layer, and that suggests a hybrid effect where the greater or the smaller the proportion of the carbon relative to the glass, the higher strain you can go before it exhibits a compressive failure. Nevertheless, the failure still at the end of this, although we've got a large nonlinearity, quite a lot of pseudo-ductile response, at the end of the test, it still fails in compression. So what can we do about that? Well, one thing we can do is to put some glass on the surface and make an asymmetric hybrid. So now we have S-glass on the surface, and then we have a fragmenting carbon hybrid here. We can still get the gradual response in the carbon, the fragmentation and the gradual failure, but avoid the catastrophic compressive failure occurring on this surface. So putting the glass there shifts the neutral axis and then allows this gradual failure here without getting a compressive failure. So initially we did this with unidirectional material. We use the same S-glass material as before, but now we've got a carbon hybrid, and essentially it's layers of M55 high modulus fibre sandwiched between pairs of T1000 intermediate modulus, which have a higher tensile strain to failure. And layups here, so we have a number of 10 repeating blocks of M55 between the T1000 and 7 layers of full thickness glass. So first of all, this was very successful in suppressing the compressive failure. We did not get any compressive failure at all. And we did see a very nice gradual tensile failure with progressive load drops. And what you can see on the response here, the load displacement response, is that we're getting a change in slope here due to the fragmentation of the M55 in tension. So that's gradually fragmenting up to the point here where finally we reach the T1000 failure strain on the tension side, and the first T1000 ply fails and then it delaminates. And then we can go a bit further and the next fly fails and that delaminates. And then progressively we can continue loading, and what happens is it progressively fails through the thickness on the tension side, but still remains intact. And even at the end of the test, the specimen is still in one piece. So we get very large deformation. The specimen is still intact. At the final point, it just slips between the rollers and we can't apply any more displacement to it or any more load. And when we take it out of the test rig, you can see that it's now basically flat, but you've got these spears of the carbon fibers from these parts here, which have failed progressively through the thickness, but the rest of the specimen is still intact, and it can still carry an appreciable load despite the gross amount of damage which has been induced. So this is exactly the sort of behavior that we wanted. So then we can do the same thing with a quasi-isotropic instead of a UD layup, and these specimens have a similar ratio of glass to carbon, and the carbon sublaminates are similar, not exactly the same as the ones in the previous picture I showed. In this case here, we just have a single M55 sandwiched between 2 T1000, and this laminate is repeated through the thickness. So we have a 0 plus minus 60, 0 S-glass, and then we have 60-degree ply with T1000, M55, T1000, then a -60, and then a 0, and that's repeated 6 times through the layup. And with these, we see a similar overall response, these quasi-isotropics compared to the UD. Similar mechanism. Again, we get this non-linearity occurring here, and then we get progressive load drops, and the specimen is intact at the end of the test, and potentially can give us a very high energy absorption. So what are the benefits of this ductile or pseudo-ductile behavior? So by putting this sort of behavior into the material, we get a warning of overload or impending failure. We get non-catastrophic damage, and we also have a detectable stiffness change. This gives the ability to carry load after this so-called failure initiation point until the structure can be repaired or replaced. We can also potentially exploit a greater proportion of the fiber's ultimate strain. So design strains are typically quite low because people are worried about damage and about catastrophic failure. To avoiding these sorts of problems, design strains are very low, well below what the composite will take. And our plan with this is that you can actually use a bit more, because you can, so long as you keep below that pseudo-ductile limit, then the specimen remains intact, is not damaged, and this has many benefits. For example, with the load distribution around the stress concentrations, provides notch sensitivity. And this should also make the materials less sensitive to defects and enable large amount of energy to be absorbed. So in conclusion, I've shown that the ply fragmentation creates a pseudo-ductile response and gives us notch sensitivity and tension. We have very good fatigue performance, no damage if we keep 80% even after 100,000 cycles. And if we do statically overload those specimens, they will slowly delaminate, but only over quite a large number of a few thousand cycles. We found that the fragmentation and non-linearity can also occur in compression, depending on the fibre, but certainly for the M55 high modulus fibre, we can get a fragmentation and non-linear response. The challenge is when you have a bending application, you have both tension and compression. So it starts to get quite complex, and the compressive and tensile failure strains are different. So you need some careful design to get the sort of response you want. We've demonstrated we can get a nice gradual failure also in bending, and that if we put a surface glass layer, then we can eliminate the compressive failure and give a very high nonlinear large deformation response with high energy absorption. So in summary, we've shown the good performance in tension, compression and bending, and I believe that these fragmenting hybrids are very promising as a potential different way to take advantage of the good properties of composite materials whilst avoiding catastrophic failure, providing some warning and an increased margin of safety. So there's some references, a lot of papers have been published on this, and these will be available. And thank you very much for your attention. I'm very happy to take questions.
Thank you very much, Michael, for this very nice presentation. So to update everybody, so you can ask all your questions on the Q&A, and then now I will start addressing some of the questions on the Q&A. And for the panelists, of course, you can raise directly your hand, and then we are going to, you can unmute if you want to ask directly your question. So if I start with the Q&A with a couple of questions about the technique for hybridization. So the first question, Michael, is about, there are different ways of hybridizing the material, and here you are choosing to make the hybridization between different layers. Why do you choose this technique? Could you achieve the same thing by hybridizing the fibers, for example? So this is the first question from the Q&A, if you want to address it.
Yeah, so it's a very interesting point. We asked ourselves the same question. It's actually very difficult to create a hybrid at the level of the fibers. So we did try. We did create some, but actually it's very difficult intersperse the fibers. So you tend to end up with not true hybrids at the fiber level. So that's the first point. However, one of the things we found with the HyperDiff program, when we use these short fibers, is with those short fibers, we can create a hybrid at the fiber level. So we get a true, because they're not continuous fibers, they intermingle very well. And so we can create very nice fiber level hybrids using that technique. So there's been quite a bit of work we have published on that, which I haven't touched on today. But we also need to keep the plies thin. So it's quite, to get this mechanism, if you hybridize at fiber level, then you get some benefit at that level. But actually in this case here, we're getting the delamination occurring and the fragmentation at ply level, which actually has some advantages in creating some additional pseudo-ductile strain. So I think both approaches can be done, but it's quite difficult to actually achieve full fiber hybrids. There's also alternatives. You can do it at toe level, but we think that doing it at the ply level is probably the best and most flexible way. And also it's relatively easy. You can make prepregs. You can combine these thin plies together to make a pseudo-ductile prepreg by putting the different fibers together and creating a material which can be used very much like current prepregs.
Very good. Thank you, Michael. We have a question from Vivek Singh about the dynamic effect. So did you make the test, did you test these hybrid composites under dynamic loading, and how does the response evolve with the dynamic effect due to the viscoelastic response and everything to the rate dependent effect?
So for these types of material, we have done some high-speed tests, and there is a paper on that, which I've not included here. And we found that for these hybrids, it doesn't make very much difference, because the fibers are not very rate dependent. Glass ones perhaps a little bit, but the carbon are not very much. We see that we still get this same fragmenting mechanism under high rate loading as well.
Okay. One question from Mohamed Saleh from Delft. So he's saying that it's good to see the benefit of increasing the strain by 1 or 2% for composite materials, but how is this comparable or compete with metals being used in applications nowadays? So it's a little bit challenging. So I think the question is, you have metals that can also show some dissipation and plasticity and things like this. How does it compare now compared to metallic applications? Yeah.
Well, the main advantage to me is weight. I mean, yes, metal is a very good material and it does show very nice ductility, but it's heavy. And also, as we heard yesterday, 2.5 trillion pounds a year, was it dollars a year on corrosion? I mean, corrosion is a real problem with many metals, and so I think composites still have a lot of advantages, and that's why we think this is an interesting approach.
That makes sense. I have a question from me actually. Since most of the ductility now is coming from the fragmentation of the carbon layer, is there a way to go, to even get more fragmentation by introducing specific defect in the carbon layer from the beginning to make sure that you go above the fragmentation rate that is guided by micromechanics? What I mean is that if you just fragment the layer like this, you get a maximum fragmentation that is guided by the micromechanics. But now if you start to introduce defect in the 0-degree layer, maybe you can go to higher quark densities and to get even more fragmentations and even more dissipations and everything. Is it something that you are looking at?
So I think it's a very interesting idea. I think there's scope for a lot of further work in this area, and maybe we can collaborate on this. Interesting. We have done little bits where for example, we have pre-cut the carbon fibers. So rather than putting continuous carbon fibers in there, we pre-cut them, and that gives us another parameter to vary. So because we can get the delamination starting straight away if we wanted, because the fibers are already cut. But we've really only just scratched the surface. One of the things about this is that there's so many different combinations. And as you saw, I showed quite a few different materials. The number of permutations is very, very high. And what we really need to do is develop even better tools for designing so we can really take advantage of this. We've done some initial work. I showed you the damage mode maps, but we haven't really yet got a full analysis prediction where from first principles we can really design the materials. I think that would be a really exciting topic to work on.
Sure. I see that we have a question from Professor Kumar. Kumar, can you hear me?
Yeah. Thanks, Professor Wisnom, for your wonderful talk on architected composites. I have a couple of questions. So if you increase the modulus mismatch between the matrix and fiber to SIS 1000, typical of, continuous carbon nanofiber reinforced epoxy, do you expect a substantial change in the failure map you just showed in the beginning of your talk?
So I'm not sure I quite call that. You're talking about using higher modulus fibers.
Yeah, exactly. So typical of, say, carbon nanofibers.
So it certainly will change. Those damage mode maps depend on all the parameters. So it's a bit hard to say exactly how they depend on the modulus. What's most important really is the failure strains, the relative difference in the failure strains. The modulus, of course, does affect that as well. And the ply thicknesses are important. So generally, when you have a higher modulus fiber, then you have quite a different failure strain. Typically, failure strain reduces on these high modulus fibers. So that probably has a bigger effect than the modulus itself. But there's a lot of potential to design and tailor these materials depending on the particular properties of the fibers you want to combine.
Yeah, my second question is, have you had a chance to explore architectures to benefit from the size effect of such, small scale fibers? Because typically I see carbon fibers here, which are microscale fibers. So, it's primarily from the architecture, of course, for a fixed, material properties. But then if you used really carbon nanofiber, probably you could even benefit from the size effect. I'm not sure if this is of interest, and I'm not even sure if you could really develop an architecture which performs optimally in all three different loading scenarios. If my understanding is correct, you looked at bending, tension, and compression separately. But if you had to combine all these three things, can we achieve a global optimum performance? And is there an optimal architecture which could really lead to overall, optimal performance?
Well, it becomes quite complex, as you've shown. Yes, you've got additional variables here, so it means that you've got more parameters to vary, and it's perhaps more difficult to achieve the optimum. You need a particular application, because for different applications, that optimum is going to be different. If you've got an all tension application, it's easy because you don't need to worry about the interaction. If you've got bending loads or both tension and compression, clearly you've got to be able to deal with both of them. So I think it makes the problem more challenging to design, but I think the possibilities are there. And so you were asking about the high modulus. What was the first part of the question about the high modulus fibers?
Oh, I was just asking you whether you had a chance to explore architectures to benefit from the size of yeah.
So we haven't done anything with looking at that in this part of the program. I'm looking at nanofibers, but it's very interesting that what happens with these thin plies. So the high strength fibers that we use for quite a bit of the work I've shown today normally have a failure strain of about 1.6%. Well, it's about 1.8% if you measure it very carefully with a good test. But actually, we find in the hybrids, if they're very thin and we have only a single 0.03 millimeter ply, that 1.8% failure strain goes up to 2.3%. So a very substantial increase in the failure strain. And I suppose you could consider it a sort of size effect, but what it's really about is the way that the carbon fails by a critical cluster of broken fibers. When you have a hybrid with very thin plies, it's very difficult to form that critical cluster because you don't have enough fibers. And if you do have a weak fiber, it's only eventually probably only got 2 fibers through the thickness. So it has to form a cluster in the side directions only, not in the through thickness directions. So you inhibit the ability to form a critical cluster, and the failure strains are very substantially increased. So if you just take that on its own, you could take 1.8% up to 2.3%. That's a huge increase in tensile failure strain just for the same fiber, in addition to getting the benefits of the fragmentation, the pseudo-ductility. So I think it's a very interesting question, a very interesting area to take advantage of a greater proportion of the real true strength of the material.
Thank you.
Okay.
Thank you very much.
Thank you, Michael. So, we are closing now at 2:45. The last question. So we have Hussein, you have a question? Hussein, yes, sir? Who was the
Yeah.
question?
Yeah. Sorry. Thank you for this interesting presentation. So my question is, I see that you use to measure the strain gauge with cable. So my question, this cable affect your measurement? In other way, if you have the opportunity to use sensor without this cable, is better for your measurement or didn't affect very well the measurement?
I don't think it affected this case because the specimens are pretty stiff and the strain gauge and the cable are not very significant. But it's a good point that you do need to worry about this. I remember when we did work on just resin samples, the strain gauge made a quite significant difference to the stiffness of the specimen. But for these composites, I don't think it does. We've used video extensometers usually as well as strain gauges, and we get very similar results.
So, and then thank you, Hussein. So we had one question from Sanjay, but he lowered the hand, so I think he got the answer. Vasilis, you want to give the last question? Professor Kostopoulos?
Thank you very much, Professor Wisnom. Really excellent presentation, very nice ideas for hybridization and introducing plasticity. Just to ask two things. First of all, composites are very sensitive in the interlaminar fracture toughness. So this means this promotes the lamination with low impact loading. Does this combination promotes the lamination resistance or doesn't affect it? And the second is, in case of low velocity impact, does this configuration absorbs more energy than in the case of just carbon or glass combination?
So these are really very interesting questions. Unfortunately, I can't give you a full answer because we haven't done enough work yet. I think it's actually very complex. The behavior and impact, we have done impact tests. The behavior is a bit different from ordinary composites and quite complex, and we haven't really quite got to the bottom of what controls it. So what I can say is that indication. So you're absolutely right about the fracture toughness is really important, and I didn't mention it really, but the whole behavior of these materials depends on what is the mode 2 delamination fracture toughness. So if you have a tougher material, then the critical ply thickness to get this sort of response becomes higher because you need to get a certain amount of delamination, but not too much. So the fracture toughness does come into play. In terms of the effect on impact, we've done a limited amount of work, which does suggest that we might get a little bit less delamination under impact loading, but I wouldn't really like to stress that too much because we haven't done enough yet. So what happens in terms of impact and compression after impact still needs to be looked at, but there are some indications that the behavior will be quite good, and we have already shown that we get reduced knot sensitivity in tension. We haven't actually looked at that in compression, but I would expect, because the mechanisms are quite similar, I would expect that we'd also see resistance to damage in compression as well. So I think there's indications that it will be good, but it's too early to say yet.
Thank you very much.
Okay, thank you very much to everyone.